Hey Chemistry Crew, Mr. Collier here. I'm going to be going over pages 23 and 24 in your gases packet, where we are continuing working on the ideal gas law, some more problems there. So the ideal gas law says PV equals nRT, so the pressure of a gas times the volume of gas equals the number of particles times the gas constant times the temperature. Okay, so what I'm going to do as I go through these problems is maybe not go through every problem completely as they're starting to get kind of same, but show you some of the kind of process here and there and some of the twists and turns that you might see. So number 10 asks what pressure, okay? So the first thing I'm going to do is take PV equals nRT. I'm going to rearrange it to solve for pressure, and that's going to give me this equation here. From there, I'm now going to find the rest of my numbers that they've given me and plug them in. So they give me 0.1 moles, that's my number. I'm going to take my gas constant, plug that in where it goes. Next, I'm looking for a temperature, 500 Kelvin. Boom, there it is. And a volume of 10 liters. Plug them in, spit out an answer, check for sig digs. The 0.1 moles limits my sig digs to just the 2 that I gave. Number 11, what volume? So again, I'm going to take the same equation, rearrange it for volume, look for the other values. We've got a pressure in atmosphere, a number of moles, and a temperature in Celsius. So the only real conversion I had to do there was change my temperature to Kelvin. Atmospheres and moles were good to go. Make sure you're putting things in the right place though as you rearrange these equations. Number 12, now here is something that shows up a few different times. Rather than talk about moles of a gas, we can tell you grams of a gas. When you're talking about grams of a gas, you know how many moles it is. You just have to do a simple conversion. So this is carbon dioxide gas, which has a molar mass of 44 grams per mole. So I can simply do a grams to mole conversion to find the number of moles. Now I'm ready to use the equation as normal. I know volume, I know pressure, and so we're looking for temperature. So I rearrange for temperature, get my other values, start plugging them in, and I'll get my final answer. Number 13, how many grams? Okay, so again, here's one where we're going to need to do some molar mass conversions, but when I'm looking for grams, that triggers the fact that I'm looking for how much of this gas do I have. So I'm solving for N, so I rearrange for N. Now I go back and start looking at things. I've got millimeters of mercury, that's my pressure. I need to convert that to atmospheres. I didn't actually show the conversion here, but that's 2 atmospheres if you do that conversion. I've got milliliters, which I turn into liters, and I've got temperature in Celsius, which I convert to Kelvin. So this one actually had 3 different conversions. When I plug those values in, I am going to get 1 mole of gas, and that's kind of on purpose. We picked those numbers, and 1 mole of gas, I can figure out how many grams there are if I multiply by the molar mass of oxygen gas, 32 grams per mole. Tells me I'll have 32 grams. Number 14 gets a little bit tricky with just the way the numbers look, but it's actually not that bad. So this is talking about when we pull a vacuum, how we can get really, really low pressures. So we can't get all the way to 0 pressure, perfect vacuum, but we can get pretty close. So here, this pressure is 1 times 10 to the negative 10th millimeters of mercury. So it's a very, very low pressure. And we want to know how much volume that gas would take up at normal pressures and normal temperatures. So we're looking for volume, milliliters, and we have the number of gas molecules, and we know we are looking for standard temperature. So there's a lot going on here. Okay, so the first thing I want to point out is if we know how many molecules of a gas we have, the actual counted number of molecules, we actually know how many moles that is, but it's one we haven't done yet on this worksheet. It's been a while since we did it in class, but we actually know how many molecules make up a mole. It's 6.02 times 10 to the 23rd molecules. If I had that many molecules, I'd have a mole. So I simply take the number of molecules I do have, divide it by the number of molecules in a mole, and that'll tell me how many moles I have. It's a very small fraction of a mole because we have a very small amount of molecules in the grand scheme of things. I know 1 times 10 to the 6th is a big number, but it's a very small number of molecules considering how small molecules are. So that gives me my moles. The other thing I need to do is convert this millimeters of mercury that they gave me, which again was a crazy small number, but I need to convert that to atmospheres because this equation requires atmospheres. Doing that, I'm very now close to getting the final answer. I just need to plug my values in. So I've solved the PV equals nRT for volume, and now I'm plugging in my moles and my converted atmospheres or pressure. And then of course, standard temperature is just 273, and there's my gas constant, and that'll spit out the very small volume that this takes up. So you can see we can do some various somewhat complicated problems here. That was 23. Here on 24, again, using our equation, it's a lot more of the same general idea. What volume? So I'm going to solve for volume. I'm going to take my 100 grams of oxygen gas, divide it by the molar mass to figure out how many moles, plug that in. Gas constant, temperature in Celsius needs to be converted to Kelvin, divided by the atmospheres, the pressure, and get my answer. Okay. Something I will often do, and here you can see me doing it in number 16, is just sort of underline numbers and write what variable they represent above them. So there's a volume, there's a pressure, there's a temperature, right? We've got a new pressure and a new temperature. So what's the new volume? Well, so here's a little bit of a trick. You're in the middle of an ideal gas law problem, and here I snuck in this combined gas law problem. So hopefully you realize that, but if not, that was the trick here. Now we're starting to throw in some different types of problems at you. So this is P1V1 equals P2V2. Aside from the fact that there was like more numbers than I would have needed for a PV equals nRT problem, the other real key thing here on this one is that it gave me two different pressures and two different temperatures. Anytime you have changing conditions, a before and an after, you're going to use those earlier gas laws, the Boyles and the Charles, and in this case, the combined gas law. And once you realize that, hopefully it's pretty straightforward. Pressures times volumes divided by temperatures before equals pressure times volume divided by temperature after. Solve for whichever one you don't know. 17 is another one of these where I snuck in a combined gas law problem. Again, you know this because there are two different volumes, two different pressures, and you're needing to solve for them. One other thing that I want to mention here is that while the volume is in cubic centimeters, that's actually equal to a milliliter. Those are the same thing. That was in the notes early on. All right, 18. I slip right back into a PV equals nRT problem. In this case, we want to solve for temperature. We know the mass of helium, which means we need to do a molar mass conversion to get the number of moles. The pressure is in atmospheres. And the volume is 1.25 liters. Looking for the temperature in Celsius. So we're going to solve for temperature, plug in our atmospheres, our liters, our converted moles, and our gas constant. We get out a temperature, that's going to be Kelvin, subtract 273, and there you have your Celsius temperature. All right, last two. In 19, we're solving for N, the number of moles. How did I know that? Well, this one straight up says how many moles. So that one's pretty straightforward. Couple things we do need to consider. The pressure is in kilopascals. So over here, I converted that into atmospheres. That's actually the only conversion you really need here. Oh, no, sorry. You also need to convert Celsius to Kelvin. So two conversions, the pressure and the Kelvin temperature. Number 20, how many grams? So again, I'm looking for N, the number of moles, but I'm going to have to convert it to grams at the end. How many grams of argon would it take to fill a light bulb with a volume of 0.425? So traditional light bulbs have these filaments in them that will like literally catch on fire and burst if they're not, if they're in like an oxygen-rich environment. So inside a light bulb, they will replace the regular air with things like argon or nitrogen that will not react. So we want to know how much they need. And this is at standard temperature and pressure. If we want the light bulb at standard temperature and pressure, although I think sometimes they have lower pressures inside of light bulbs. So here we know that the atmosphere is 1, the pressure. We know the temperature is 273, and we want to figure out the volume, or knowing that volume that's given, how many moles I solve for moles. I multiply it by the molar mass of argon because that's the gas in question. And I'll find how many grams of argon they need to pump into that light bulb. Of course, as I mentioned previously, all the answers are at the bottom of the page, so you can kind of see how you've done there. But that should be everything you need for pages, I think, 22 and 23. Let me know if you have any questions.